Now we give the floor to our colleague Damijan Cerinski from Veski, part of the Dewesoft family.
Yeah. Thank you very much. Yeah, just try. Okay. Yeah, thank you very much for the introduction. So I'm gonna give you the presentation about one study that we performed. It's actually one Francis turbine runner has cracked in the operation. And since it's not the first time that happened, this time we try to find out what is the root cause and try to avoid it in the future or monitor it to see what can we do about it. So for the introduction, this is a pump storage turbine runner that cracks and eventually leads to irreversible damage and subsequent replacement, and you can imagine a few months out of work. So here on the picture, I believe this, yeah, you can see when it was still installed, the part of the runner completely broke. So and they found it later in a draft tube. And here's some basic information about the unit, which will be significant for our analysis. So the nominal rotational speed is 10 Hertz, and this turbine runner has 7 runner blades, and it's 16 guide vane blades on this unit. So on this unit, we have actually installed our machine condition monitoring system over the years, and we track a lots of data, a lots of sensors we have there, relative vibration, absolute vibration, we measure air gap and everything. And even though the damage happened, when we after that look at the data, even before that actually, that we look at the data, and there is a certain start of growth of the turbine guide bearing relative vibrations, but the values were still really, really low. It was in the zone AB, so the plant personnel call us, okay, something's happening, let's analyze that. We were doing that, but unfortunately we didn't do it on time, because even though this jump looks quite high, it's not. This was way below the values prescribed by ISO standards. So after this happened, we go deeper into the analysis to see what happened. Since I already explained, we have the data for I don't know, 10 years before that, and we actually see that when we're looking the spectrum of the relative vibration, absolute vibration, we measured the absolute vibration on the turbine cover. We found out that at some point, I think, for example, 2 years before the complete damage, there was a scene of the 16 harmonic of the nominal speed, so 160 Hertz. There was a component occur, which is actually the 6. So it's a 6 guide vanes multiplied by nominal rotational speed of 10 Hertz, and this was actually indication when some first small crack occur on the turbine runner, and this is indication when some small crack occur. After that, this 16 harmonic start to grow as the crack propagate, and this was caused as one of the main indication that something happened. But before that, there was also 130 Hertz, which actually second multiplier of the runner blades multiplied by nominal rotational speed. This was always there. We were aware of that, and actually this is probably the reason why it eventually break. To confirm this was actually let's see what we have from the analysis. We have at 140 Hertz always the component. We need to see if there's some resonance and why is that happening, where it comes from. So to explain this, to correlation between this 140 Hertz excitation, we made a bump test to identify the natural vibration mode of the runner structure and to be completely sure that this is the case, what happened here. To do it, we actually do it in 2 ways. First, during the replacement, the new turbine came and we did the bump test measurements only on the turbine runner. So it was not connected coupled to the shaft or anything, and we did the first measurement. Few months later, when it was the runner coupled to the shaft. We repeat the measurement. This is from the draft tube, and also we put some accelerometers also directly on the shaft. This is above the turbine, and you can see me hitting the shaft with a rubber hammer. And here is the Dewesoft equipment which we use for the measurement and do the analysis. So first results are the free turbine runner results, and we can see that the lowest frequency was around 257 Hertz and one was 329 Hertz. And here's some vibrational modes that occur at these frequencies, which is quite higher than 140 Hertz. After that, the runner was coupled to the shaft, and we, as I explained, repeat the measurements. And it was, we have a little, I will not say problem, but its power plant has 2 units that works. Of course, the second unit was working, and we have some interference from this around 100 Hertz because everything is quite close. So we have to do the corrections. So we measure measure and calculate the frequencies that's already on the shaft and the turbine runner when we don't hit it. So this is some vibration that's already there, and when we hit it and do the bump test, we remove these frequencies to get a clearer picture what actually happened. And it was quite interesting that we get a completely new natural frequency which was not there before, which is around 174 Hertz. This upper side is the turbine runner itself, and below is the results from a turbine shaft. And on the turbine shaft, it's clearly seen that this frequency is really first peak that actually is here. So final remarks, we just then analyze everything, and when the runner is free, the outer and inner edges are completely free, and only some symmetrical vibration modes can occur, so we could not see these 174 Hertz. After the runner is coupled to the shaft, the lowest asymmetric mode is at 174 Hertz. What's the meaning of this? Actually, when the runner is coupled to the shaft, a completely new system actually is there, and actually we concluded that we recorded that from the results when we're hitting the shaft. Actually, the whole generator, so the turbine runner, the shaft, and the generator above, they all have a natural frequency at 174 Hertz, and this is quite close to 140 Hertz, because when we add this, of course, completely dry, it's not running, we don't have water. When there's a lot of water coming to the turbine, the water mass will decrease this natural frequency for sure. We don't know where it will end, we cannot know that, but our assumption is that it will drop around 140 Hertz, which is then quite bad. And one more conclusion is that when we are measuring, as I explained, a lot of things on this unit, we see this 140 Hertz on a relative and absolute vibration on lower guide bearing, upper guide bearing, turbine guide bearing, and absolute vibration on a turbine cover. So this is actually what's happened in a operation, and this could be quite the reason why the whole unit is actually in a resonance. Okay, then if we now concluded there's a problem, so the design is like it is, 7 runner blades cause you have excitation at 140 Hertz, and there's a natural frequency close to that, so there's resonance. What can we do now? So the other unit is completely the same, so both units have the same problem. And what can we do now to track this? Because obviously we have to track it. It can happen again. It wasn't the first time. So first what we do, we include pressure measurements in the turbine zone. So we installed pressure sensors in penstock, spiral casing, turbine cover, draft tube, and the vacuum zones. We put into our machine condition monitoring system the calculation of amplitudes and phase, and these frequencies, which are quite critical, which is actually the first indication of some cracks. And we actually calculate the RMS values of all these frequencies and put alarm on it. So whenever happens, the plant personnel, we get the alarm in the SCADA system, for example, and see that something happened, that we should check and do the analysis much more early than we did it before. The idea is to have an early detection of the rotor cracks. This is how it looks now. So we're tracking key parameters for early detection of the rotor cracks. Here above you can see the absolute vibration on the turbine bearing and the turbine cover, and this is these RMS values of all these critical frequencies. We have pressures. We have also measuring the strain, which I didn't mention. We put also one dragonfly sensor that you probably heard yesterday, and also measure the same frequencies from this sensor. And below this is actually the operating condition that happened on this unit. This is, I think, 2 or 3 months of data, and you can see that the action power, it's quite go up and down, and also the reactive power. So this unit goes in various operating conditions. Now we track it, and we believe that we will now much early know that something is start to happen before the root cause is completely removed from this. Some conclusions, we do the bump test, and the idea is first asymmetric mode is at 174 Hertz, which may shift to 140 by adding water mass into the count, and there's a possibility of resonance, which probably happen here, and this is it. Thank you. Any question? If you want more info, we can discuss it in more detail. Here's our booth at Veski booth, so feel free to comment. We'll discuss in detail. And now some quick question for sure.
Thank you very much, Damijan.